Good evening and welcome everybody. My name is Obi-Wan Pez and this is N-Simplex Pachinko. We are going to be doing some mathy type stuff tonight on this, the 1st of October. Hope people have some kind of idea about things that they might be interested in. If not, I mean, I have some ideas, but might not be terribly interesting to everybody else. All right. Excuse me. I think the first one that I like to do we are going to be looking at the planet Earth. And just pretend for a minute that it is actually a circle instead of, as we know, an oblate spheroid, which is pretty close to having a cross-section of an ellipse. It's not 100% accurate, but you know what? It's within error. And if we, again, just assume that it is, in fact, a has a circular cross-section. The size of the Earth is approximately 6,371 kilometers. And I would like to, first of all, look at if there were a person sat on the sat on the edge of the ocean. They were themselves 2 meters tall, not to scale. Who'd have thunk? Standing on the ocean's edge, meaning that they're, let's say, 2 meters tall at the eyes, just to make it easy. We would like to know what their view distance is. How far around the Earth would they be able to see at a height of 2 meters at the water's edge? So here, we want to know essentially what is the distance that this is going to travel out until it reaches the tangent to the circle. Oops. Now, because a person can see out to a tangent line to the Earth, we know that that is going to make a right angle with the radius, whichever radius this is. Okay, this is going to make 3, well, no, this is going to make 2 right triangles the ones we care about, which are going to be congruent to each other, so we only have to do the math on one of them, and then we'll figure it out. We'd also like to know what percentage of the Earth would you be able to see from your particular vantage point if this were you? So here we're curious about the sight distance here, which is going to be the short leg of this particular triangle. So we have here that r squared plus x squared is going to be equal to r plus 0.002. Again, 2 meters. If we're going to do this all in kilometers, then that'll work pretty well. Squared. Right, so x squared is going to be r squared plus 2 times 0.002r plus 0. And in fact, at this point, just probably use scientific notation. So 2 times 10 to the, this is negative thirds, this is going to be negative sixth. Okay, and then we take the r squared from the above equation and subtract it from both sides, so we get minus r squared, which is then going to get rid of our r squareds here and here. And now we get an expression that is only in r, so x squared is equal to 0.004r plus 2 times 10 to the negative 6, which is 2 millimeters. So we're really not going to care so much about that, but just for the sake of accuracy, we'll still work with this. X squared is going to be equal to, this is 6,371 is 25,484. With a decimal place back 3 places, it's going to be 25.484 plus 2 times 10 to the negative 6th. So that's 1, 2, 3, 4, 5, 6. That's not a 6. That's supposed to be a 2. A. Alright, 1, 2, 3, 4, 5, 6. Cool. 5 zeros before it. And then we grab our trusty calculator, which is running dangerously low on juice. I really need to find a USB-B for this thing. It's ridiculous. I swear all of them are slightly different. 25.484002, and then we will take the square root of that number. Really? Oh well. 25.4844002. We get a total of x being 5.048168 kilometers. Okay, so if you were in the middle of a calm ocean with your eyeballs 2 meters above the sea, you'd be able to see 5.05, give or take, kilometers in every single direction, or 5,048 and change meters. So what about the percentage of Earth's surface? So there's a few ways that you could go and figure this out. One is to calculate this angle right here, theta. If you like trig, this is going to be your way to go pretty much. right? So if you want trig, then you're going to want to find out what theta is here. We have probably the cosine of theta is going to be equal to, we want the adjacent over hypotenuse, r over r plus 0.002. So it is a minuscule tiny amount over 1, or under 1, excuse me. Over 1 would be bad. Alright, so 6371 divided by 6371.002, which is approximately 0.999999. 2, 3, 4, 5, 6, cool. 6861. And if we take the inverse cosine of that answer while we are in degree mode, take the inverse cosine, arc cosine, right, then we end up getting the arc cosine of that number there, which is, it's pretty thick just because I'm at 210% size, so we'll be zooming back out in a minute. Theta is going to be approximately 0.045399259 degrees. Which again, if we want the percentage of Earth's surface that is visible, I'm also having a moment here because I'm thinking, like, is that going to necessarily be true if we're not counting this in 3 dimensions, right? So on one hand I want to say, yeah, it's probably fine. On the other, I don't want to just trust it blindly, so we'll calculate it out the other way in just a sec. If this is that divided by 360... right, that degrees divided by 360 is the percentage of the circle that we're getting. So the percentage of the circle is going to be 0.000126, which then goes on, or this is a 0.01261%. of the Earth's surface will be visible to you standing 2 meters above a calm sea. Alright, now let's make sure that that's actually true by going into surface area. So the surface area of Earth is going to be 4/3 pi r. Nope, that's a volume. A 4 pi r squared. Which is going to be 4 pi times 6371 squared. So 4 pi times 6371 squared is going to be this big number, 5.1006 times 10 to the 368. And that's square kilometers. Alright, so then we want to know the surface area of the cap that we can actually see that's visible. Hmm. Uh, 2 pi RH it looks like. Where H is the internal. Hey Zach, how's it going? H is going to be the internal height of the sphere. So that's fun. Right. Okay, or we could do h squared plus a squared, but that's going to be derived all basically the same way. Oops. Oh, interesting. Okay, that's, well then. So the area of a spherical cap right, if this is the radius of the sphere itself, and h is the internal height of just the cap by itself, right? So we want to know from our original basically what's the cap height of this thing right here. Let's go with that. That's our H that we want to find. Oh man. Okay, this is going to be a right angle. We have a radius here, which is going to be our hypotenuse. And we have our angle. So, yeah, that's going to be as good as that's going to get. And then we can find h by subtracting off whatever this leg's going to be here. Now, it is similar to this one, but I don't think that we can use that number. Probably not. I'm going to guess that it's not identical, but it could be. So it could be interesting. Okay. So we want to look at this and say that the cosine again of theta is going to be equal to, in this case, our leg side is r minus h divided by our hypotenuse side is h. So we'll go with that. H then is going to be equal to, this is r cosine theta, swap sides, r minus r cosine theta, or h is equal to 1 minus cosine theta times r. That was really painless, actually. Now that I'm looking at it. Woohoo! Gotta love it. Alright, h is equal to 1 minus our cosine of theta. You know what? Let's delete that. Let's just take our answer from up here. Minus that. It's going to be that number times 10 to the negative 7th. Cool. Times 6371 is going to be equal to a 0.001999856.9. Keeps going from there. So that's our height of the spherical cap that you are able to see if you're just standing 2 meters with your eyes 2 meters above sea level. Right, that is 1.9998 meters worth of cap. And then it says here that we can use the formula area of a cap. It's going to be equal to 2 pi r h. Which is rather interesting. I don't know if anybody can see that, but that is the same as a lateral area of a corresponding cylinder. You're taking the yep, you're taking a circumference 2 pi r, which is out to the size of the whole sphere, and then multiplying it by the cap height, h. So in this case, it's really tiny. And then we end up with the same as the lateral area of the cylinder is going to be the area of our cap. That's not an obvious result, but nonetheless. Let's see, Archimedes derived the area of a sphere being 4 pi r squared, and then use the projection of a cap on a cylinder, which then allowed him to reason through stuff. Eventually, somebody worked it out with actual algebra. Times 2 pi times 6371. We have an 80.054 square kilometers. And when we take that versus the actual area, surface area of the entire planet, right? Divide that by 5. Oh, it's that number up there. Let's just drag that number again. We end up with, drum roll please, they're not the same. Right. So we can't exactly trust, and that makes sense because I'm trying to do something linear in that other one, and this is squared. What if I take the square root of this number? Do I get the other one? Alright, yeah, no. Okay, so percentage Earth's surface visible. We're going to take 80.054 square kilometers and divide by the whole planet, which again was 5.1006 with some more stuff times 10 to the 8th square kilometers. Again, that's all going away. This is going to be equal to 1.5695, some more stuff, times 10 to the negative 7th, which means that's 10 to the negative 5th as a percentage. Okay, if we take the square root of this answer, we do not get the other one either, so something else is going on that's not quite true. Alright, well, never mind with that one then. So here, 0.000015695% of the Earth's surface will be visible to you. That's a much smaller number. Alrighty. Well, it sounds like Pretzel is choosing scarier music. Let's celebrate Scary Month. Here I am using orange and black. Right. So our percentage of the surface area of the Earth that's actually visible ends up being, again, this number. 10 to the negative 5th as a percentage. So very, very, very tiny. Makes more sense than 1/100th of 1%. It is October. Woohoo! One can hardly believe, right? was looking at this Harold Jacobs question. Might be interesting. Let's get back to normal here. What is normal, really? Almost an equilateral triangle. That's fine. Okay. Two men get shipwrecked on a desert island, and one of them decides that he is going to try and rotate what spot he is trying to look for a ship to rescue him and his comrade from on any particular day. He is going to remain at one of the locations. So his goal is to build a house. In order to minimize the total distance to each point. Now it is an equilateral triangle with 12-kilometer sides. So without loss of generality, we're just going to pick one side. We're going to say that, we're going to focus on BC as kind of our primary side. So where he builds the house will be in relation to that particular side. Again, it doesn't really matter. It's going to be symmetric. So there could, in theory, be 6 different points where this could be true. Okay. So since he will have to dig up vegetation, is the motivation in terms of why we need to find the optimum placement for this house. Again, basically what we're doing is we're just picking a particular point and saying, where is it that this is going to minimize the total blue distance between all 3 corners? So, interesting question, right? Let's see. We could do it using calculus, which I think would be easy enough. Next question would be how did Euclid do this? So if we end up placing 0, 0, we're going to do algebraic geometry here. And any particular point, x comma y, it will be within the within the triangle or on its borders, but at the same time, right, like I said, we'll kind of say, man. Alright, 12, 0 is going to be where C is, and B is going to be at 6, comma, and then here we need the apothegm. I think that's the right word. No, that's from the center. We need the altitude going from B all the way down, which is going to be 6, 12. This is a 30, 60, 90 triangle, so 6 root 3. Okay. Goodness. Alright, so in order to find the distance total, we need to find the sum of the distances that are between A and, what do we call this? D? Good enough? That's a terrible idea. I'm already using a capital D on this, so E. Right? Distance of AE plus the distance of BE plus the distance of CE. Each of these can be done using the distance formula. So the first one is going to be the square root of. Here we're just dropping an altitude from E to that particular side, and we're saying, oh look, it's a right triangle. Distance across here is X, distance up is Y. So that's going to be X squared plus Y squared. Okay. Plus square root of B to E is going to be X minus 6 squared plus Y minus 6 root 3 squared plus distance between C and E is going to be the square root of X minus 12 squared plus Y squared. Alright, Y minus 0, so simplified a little bit. Alright, we do not want to square both sides of this equation, because that is going to cause this thing to become a trinomial, which then gets squared, which is going to be really nasty. Next question, can we find y as a function of x? Not really, because it could, in theory, be any point which is within the triangle. If we want to reduce this to, it has to be from the center to either side of BC, we could do that, but that's not going to give us a specific, like, it's going to give us boundaries, but it's not going to give us relationships between x and y. It's still going to be effectively any point we want. Okay, we could, in theory, take the derivative, set it equal to 0. It's going to be pretty gross, and we're going to get partial derivatives. Yeah, it's gross. You know, what else was I expecting, honestly? But, Alright, we're setting this equal to 0. Ideally, we want to find one single place where our x and y right. Multiply through by 2, so that clears that little bit out. So we could either multiply through by all the stuff in the denominators, which is going to make a horrible mess. Every term will have 2 of them. Good news, they do combine. Bad news, not well. combine dx's and dy's separately, form a fraction that is dy dx, but at the same time, I don't know that this is necessarily going to help us find anything. So we don't really want the place where dy dx is equal to 0. Right? Doesn't have to make any horizontal movements or anything like that. Hey, Sensation. Need more Van Halen. I mean, I'm not going to argue, but at the same time, I also don't want to pay royalties for it, and I do want to keep having actual... whatever, I don't know. Oh, keeping highlight streams up so we can get those posted. I finally did clear out my queue. Thank you for reminding me. I cleared out my queue of all of the things that I was meaning to create highlights for. I just sucked it up and did it the other day. So literally all of our N Simplex Pachinko VODs are now like regular VODs, but when they expire, they'll still have the highlights around. I still need to sort them into their appropriate locations, but I figure I can do that later. You know, like tonight. Woo! How's things? Oh, your way. Oh, those also all have 2s. They also all have 2s, so that's actually convenient, because we don't even have to do anything. It's just going to clear themselves out, so that's nice. Bit nippy on the heels? Yeah. Alright, so we got like x dx plus 2y dy over x squared plus y squared to the 1/2. Okay. Oh, that's not a 2y. That's gone. Plus y dy. Okay, plus... x minus 6 dx plus y minus 6 root 3 dy over this nastiness, x minus 6 squared plus y minus 6 root 3 squared. Okay. Plus third one. X minus 12 dx plus y dy all over x minus 12 parentheses squared plus y squared. Alright, all to the 1/2. Not so sure we're going to get anything nice out of this. Might have to go and program it into something to try to find a numerical solution. That's quitter's talk, huh? All right. Let's try something weird. So if we do this, we're going to end up with 1/2 derivative of A times BC. That, nope. B, C, parentheses to the 1/2. Right, A, B, and C are just going to be the inside portions. So not all of it, just that stuff. Okay, so that then leaves, we're going to do 1/2 times the derivative of B times AC, so 1/2, plus 1/2 derivative of C times AB to the 1/2. Yeah, that's probably not helping either, but puts the problem in a slightly different form. Alright, hypothesis. Is it the center of the triangle? In this particular case, right, it seems like it would make the most sense. You try to find the place where you have the least distance traveled from each, from the house to each of the corners. So with an equilateral triangle, anyway, it seems like the shortest distance would be in the center. But then I want to figure out if there's a way to show that. Alright, we'll take a think on it. Everybody take a 3-minute break, get up, stretch, do some exercises, whatever you got. And we'll be back in 3. See you in a little bit. And thanks for coming. Be right back. Welcome back, everybody. Just in time. Tonight we are hashtag not sponsored by Wiper and True Espresso Martini Shake Coffee Stout. Little tiny picture of the space shuttle. That is essentially a stirrer for the drink. I have no idea why that's there. Interesting. It is a very nice color black that I cannot see through. Alright. Yeah, so I think in this particular case we can use sort of a symmetry argument. Where if it's along any of the three edges, then we're going to end up getting if it's along any of the three edges, and we said let's prioritize B to C, then we're going to essentially okay, if it is along BC, this is going to be terrible with the use of A, B, and C as variables in the or expressions up there, but nonetheless, right? If we choose a point along ABC, that hey, Waffle Wars, how's it going? Then there is going to be a particular point, the center of BC, across which we will have an equal, like something with the same length. And if we were to put it at either B or C, that would be just the perimeter of the triangle. Like to say, okay, it's the distance between no, if it was at B, it would just be AB plus BC, being the two potential distances that you have to travel. But that's still pretty long. If we go somewhere else, like where the blue dots are, then we've got the distance BC that's getting added, and we have a shorter distance than AB. That is a D. Right, the measurement of AD is going to be less than AB, or AC for that matter, but, you know, we're concentrating on it being an equilateral triangle. So the symmetry argument holds up that going just on the other side of it, over to E, right, AD is going to be equal to AE, and so using this, we're going to be able to say, okay, look, if we take this stuff into account, then call it F, right? Then AF is going to be less than AD, and AF is going to be the optimum location. Good evening, Saltare. How's it going? Let me know how to actually pronounce your name if you're interested. We were doing some math stuff tonight. My name is Obi-Wan Pez. This is N Simplex Pachinko. Welcome in. Our community of math streamers has been growing of late, and we have... oops. There's more than one. Obviously. we have these 7 really awesome people, and then a whole bunch of others who are also around as part of our community who also stream. I can attempt to help you out. Yeah, sure. And if you go to that Discord server, I don't know if you know Penn Center, but he's one of our other really awesome peoples. Typically, we place some stuff either in the Maths forum or the Maths chat. So you can go with either of those, and probably the forum. And then we can get that answered on stream, and I'll post that we talked about it. And anybody else might decide to add their 2 cents. Depends. Because sometimes I do, so. Okay, so that is a quadratic multiplied by a linear divided by a quadratic. Is that true? And let me write it out. Alright, this is what I'm seeing. Goodness. I feel like I got something caught in my throat. It's terrible. So, if this is what the question was, correct formatting and everything, my suggestion... No worries. And I will apologize for my non-existent Portuguese. So... my suggestion with this is, would it be better, or would you know how to do it if this were an equality? So if it was equal to 0, would that make it any better in terms of you being able to understand it? No, Walrus, it's very hot. Okay. Okay, so yes, that's going to be one thing that we need to do. Now, why do you do that, is the other question. what does that help you look for? What structures are going to, what structures will that help you find? So I spend a lot of time in my pre-calculus class, which this appears to be the kind of like pre-calc, just about to do calculus probably next semester, next year, that we do at my community college where I was working for the last 15 years or so. So I really told my students that what you want to do is you want to look for what kinds of structures this whole thing is going to create. And bonus, it doesn't just do that on these problems. It does them on all problems. So no matter what you're looking at, right? Why do you set the numerator equal to 0? Like, what does that help you find? Okay, interesting. Haven't heard it put that way. So what we're going to see is that anytime the numerator is equal to 0, then those are the locations where the whole function, the whole fraction, is equal to 0. Which means these are the y values, or our function values, which tell us that we're going to get points on the graph, if you do a graph, where we're going to end up with like x1, 0, x2, 0. And we might have more. In this particular case, we have 3 answers, which you already highlighted, yes. So plus or minus 1 and x equals a half. So all 3 of those end up working out to be that particular, those particular values. So x squared minus 1 multiplied by 2x minus 1 is equal to 0 is going to imply that either x squared minus 1 is equal to 0 or 2x minus 1 is equal to 0. That implies that x is equal to positive 1/2, or that the absolute value of x is equal to 1. Which then means that x could be either negative 1 or positive 1. And then a half as well. Right, so x is equal to, this is negative 1, 1/2, and 1 are all of the locations where our zeros exist. Right, and that's really the word that we want to go for this kind of stuff, at least, in English. Right, these are the locations where that whole fraction is equal to 0. And you're absolutely right. The next step is we want to look at the denominator. And what does that tell you? If the denominator were equal to 0 somewhere, then what does that get you? Yep, no worries. Mm-hmm. Yep, we'll get there. I'm just one of those people who really likes everything to... Not +3. Likes students to be able to understand why all the stuff works. So even if you don't 100% have like the process down super well, then you could at least explain it. Alright, because the explanations are always going to be much more important than whether or not you can, perform an action. A lot of times the issue with it is that when students think that math is all about performing actions, a lot of those actions become interchangeable. They become arbitrary. It doesn't matter to them that they're doing something whenever they're doing it. They're just kind of, oh, I see a thing, and now I'm going to do this other thing that I think is the right one. They don't know why. Anyway. I'm going to keep going on my tirade about that forever, but nonetheless. Right, here we have x squared is equal to -9, and this has no real solution. Oh dear. Well, you can turn them over to my channel. Hopefully he speaks English. Or can get the closed captions, I guess. Right. So, when the denominator is equal to 0, what does that do for us? Yeah. Right. So that whole function doesn't even exist. Now in this particular case, we don't have any places where the function doesn't exist. So what this really means is there's no real solution. I should probably get rid of that. In this case, what we're doing with the denominator is we're checking to see what real numbers need to be excluded from the function itself, right? So there's no real exclusion for this particular function because our denominator will never be equal to 0. So all real numbers are going to be part of our domain, right? So domain is that x is going to be any real number. Okay, so now that we know that our domain could be any real number, now we say, okay, what we really care about is where our function, yep, we don't need to worry about the denominator in this case, because what we're really doing is we're saying, when does our function change from being positive to negative or negative to positive? When does it change? So if we've got a domain that's all real numbers, then this means that if I have a point that's down here, and then I have a point that's up here, right? What is our function doing? Yep, if I have a point that's down here and a point that's up here, then what is our function going to be doing at some point in between? Nope. I shouldn't have done it in green. That's my fault. Right? Let's just pretend those are going to be the points. If we know there's a point here and we know there's a point, we know there's a point here and we know there's a point here, right? What's that function going to be doing? And if that's a very vague question, then I understand. That's okay. So we have a property in English that's called, goodness, mean value theorem? Is that the one? Hang on. Not really. That one. Yeah. Intermediate value theorem. There we go. Okay. Now the intermediate value theorem says that if we have a point that's at this level and a point that's at this level, and we have a continuous function, which in this particular case we do. Then all of the values that are between here and here must be used at some point. So if we have a function, right, we have to get from here to here in some way, shape, or form. Right? It's a continuous function, so it has to go through all of those points. Now, it doesn't say whether it has to go like this, or like this, or as a straight line, or whatever, some other silly arrangement of the values that we're using. It doesn't matter, but the function is continuous, so all of those points need to be used at some point. Now, usually, we do this in pre-calculus and in algebra to say, well, that means that there has to be a 0 somewhere in here, because in order to get from our low point to our high point, we have to cross the x-axis, and since it's a function, we can't go like this, right? That's not allowed. If it's a function, it has to have some sort of movement from here to here that is continuous. And then we say, oh look, there is a 0. Okay. So, for what we're doing is we're going to be looking for where do the change in signs possibly exist. So, where can a function change its sign? Well, one place was the zeros. So, if we have a 0, it goes from a negative to a positive, or from a positive to a negative. Right? Most of the time. We'll talk. So using this, we say, okay, we've got 1 at -1, we've got 1 at 1/2, and we've got 1 at 1. True, but those are going to be the y values. Right now, I'm using a graph, which maybe you don't care about, but I do tend to like it a bunch. I'll show you a table method in just a minute. Okay, with this, right, we know that those are the zeros of this function, so it's going to likely change where it is in the along our axis. Is it above, where it is part of our solution, or is it below, where it's excluded from our solution? Okay, so what we do now is we say, if these are our zeros, where else could we magically disappear from the negative section and reappear in a positive section? Well, that's any time that we have a discontinuity. And what we're looking for is, where could we have had discontinuities? These are the denominators equaling 0 here. Right? If we had a location where it was discontinuous, then it could have disappeared going down and then reappeared coming from the top, and then magically it'd be in the positive region. So this would have to be part of our solution, this part would not. In this case, this is a continuous function, so we don't have any of those places where this magical disappearance act happens. Instead, what we get is that this needs to make a single curve that starts from negative infinity, goes to positive infinity. So we want to know what's the behavior. Okay? We need some test values, or in this particular case, we only need one, really. What happens when x is equal to 0? When x is equal to 0, we get -1 times -1 divided by -9. Yep. No, I know which method you're using. I'll get to it. Like I said, just a minute. Alright, this is going to get us -1/9, which is down here. Alright, now here's where it actually works. We know that this is a continuous function. The zeros themselves were all linear. So x plus 1, x minus 1, 2x minus 1, right? All of them were linear, which means that on one side of them they're positive, and on the other side they're negative. If we'd had something like x plus 2 parentheses squared, then this would have the right? This would have the same signs on the opposite sides. Either they're both negative or they're both positive. It's all to do with this number. If it's even, it's the same signs. And if it's odd, these will have opposite signs. So in this case, these have to have opposite signs, which means that here we have this negative 1/9, 0, negative 1/9, and then it goes up to 1/2, comma 0. So this is in the negative region. It has to then pass into the positive region. This then has to come back down and pass through into the negative region. And going the other way, this is in the negative region. It has to go up and pass into the positive region. Then we know for a fact that this will never cross the x-axis again, and it is permanently continuous. So this has to stay in the negative region. This has to stay in the positive region. There's no way for it to change again. And in fact, in this case, right, we have cubic in the numerator. Yeah, 1, 2, and 3, and a square in the denominator. So actually, this is not going to move like that. It's ever so slightly different. This is going to have a linear this is going to have a linear asymptote. So it's going to look something like this. I don't know what it actually looks like, but if you plug it into your calculator, you can get it. And we'll do it in Desmos in just a couple minutes. Yep. Okay. So that's going to tell us that the solution regions are going to be here and here, which are, x is going to go from negative infinity to negative 1. Up there we had greater than or equal to, so that's going to include that, union with inclusion from 1/2 to 1. So this should be our solution, which again you posted a couple minutes ago. Okay, now if we're going to do the table, right, we do the exact same thing. Less than negative 1. Because what's happening in the function itself, right, our x squared minus 1, that term, as x gets really, really big in the negative direction, is going to become a positive number. Then the 2x that it's attached to is going to become a negative number. So a positive times a negative is going to be a negative. Then at the bottom, we have a negative x squared. X squared is going to get really, really big, and then it's got a negative sticking in front of it. So now it's going to be a negative divided by a negative, which is a positive. Yep, negative 3 times negative 3 is 9. So same deal. It's just think about it in terms of what kinds of numbers are going to come out. You don't necessarily have to come up with an exact value every single time. but sometimes it helps to at least visualize. If you want to do it with the table, again, what we're going to do is look at taking the zeros that we had, and this includes all zeros and all discontinuities. In this case, the zeros are the only things we actually need. We discussed this before. So we've got -1, a half, and 1 are the terms that we got. We don't want to use those numbers. Sorry. I forget sometimes how I do this because I don't use it all that much. Let's see. So x plus 1 to x minus 1, x minus 1. Can't remember if this is how I did it. Negative x squared minus 9. Right, so then what we do is we say, using this table, then we put all of it together at the end, and we get the result. So here, what we do is we put our test values. So we want to do something that's negative and significantly more negative than our term. Again, here is x equals -1, x equals a half, x equals 1, and null, right? There is no solution for this one, no zero value, so we just want to know what's going to happen. Now there's a couple of different ways to do it. One of the ways is just what sign is this going to be? So plugging -2 into x plus 1, you're going to get a negative. Plugging -2 into 2x minus 1, you're going to get a negative. Plugging -2 into x minus 1, you're going to get a negative. And plugging -2 into negative x squared minus 9, you get a negative. The result here is multiplying the first 3 and dividing the last one, which actually is the same as multiplying all 4 signs together, and that's positive. -2 is going to be representative of all values less than -1. Yep. Go for it. Then, why redo work? Right? We could do 0. We already know what answer that's going to get us. It's going to be a negative value. So here, this is going to be positive value, a negative value, a negative value, and a negative value. That's going to get us a negative overall. We need something that is between a half and 1, so 3/4. And then we need something that's bigger, so 2. Cool. I'll take a look. Maths chat. So you're using the same numbers on both of your axes there. You have the -1, a half, and 1 on both sides. So like I did here, you've got your -1, you've got your half, you've got your 1, but then going the other way, right, because if you plug in those numbers, you're always going to get 0. Right? If you plug in -1 for -1, you get 0. And then anything you multiply by is going to be 0. And you do get a negative and a negative, but still. So here, we select values that are not zeros, where the function exists and is continuous, and is representative of all the values in that region. Right? So we know that all the values between -1 and +1/2 must have negative y values. Because again, the function is continuous. It has to go through -1, go from positive to negative, and then at 1/2 it's going from negative to positive again. So up here with our graph, right, we're looking at all this stuff ends up being negative here. Doesn't matter what point you pick. Any of those points, if you plug them into all the terms, the result ends up being negative. Right? 3/4, we get a positive here, we get a positive here, we get a negative here, and we get a negative here. Keep in mind, right, negative x squared minus 9, you're always going to get a negative anyway, so we just fill in the last one. It doesn't matter. Right, and then with 2, we get a positive, and a positive, and a positive, and a negative. So that one's going to be negative, that one's going to be positive. Yep. So, always watch out for your zeros and watch out for your discontinuities. It is possible and probably likely that you will change signs at each of those. Now, like I said before, if you have something with an even, we call it multiplicity. Then this is going to have the same signs. So if we had here, negative 2, and then we wanted -3 and -1 like that, then whatever this ended up with, if it's just this one, for instance, then we're going to get a positive on one side and also a positive on the other, because our function is going to do one of those. Right, so this is, yes. So keep in mind, your column that includes negative x squared minus 9 never changes, right? This is always negative. So realistically, right, it doesn't matter what the values are, because negative x squared minus 9 is always negative. So all it's going to do is it's always going to change whatever you had from the previous 3 columns. So here, negative, negative, negative would be a negative. Then this one changes it to be positive. Here you have a positive, negative, negative, which is negative. Nope. Sorry. Which is positive, but then we multiply by another negative, and it flips it to become negative. Positive, positive, negative should be a negative, but then we have this one, which is always negative, which flips it back up. Right? So if we actually look at Desmos, and sorry for everybody who was just staring at the screen and got blinded. If we look at the denominator, right? This is a negative x squared minus 9. These are the values of the denominator. So the denominator will always have a negative value, and it's going to start from -9 and then go down from there. So our denominator always has a big negative number in it. Okay, so it's not that the denominator doesn't exist. It's that there is no 0 in the denominator, and so the function itself will always exist. The maximum, yeah. So the vertex there, the maximum, is going to be at -9 when x is 0. So it never makes it up to this level here, y equals 0, so that it could flip the signs. It's never going to do that. It's always going to have a negative value itself. Right, so we had, what, x squared minus 1 and 2x minus 1. Nope, minus 1. Right, mute that for a sec. So we've got, this is our numerator, and this is telling us that we have here, at -1 we have a 0, at a half we have a 0, and at +1 we have a 0. So those are all the places where the signs change. Or at least, again, could change. Then we actually verify it, and we say, here's where yes, they do change at all of these locations. Or you check the multiplicity, right? Our multiplicity is x equals 1, x equals -1, have a multiplicity of 1, and x equals a half has a multiplicity of 1. So because it's multiplicity 1, look at it closely, right? If we were to zoom in, what kind of function do you see here? What does it look like? No. When you zoom in, right? This is x at our line, or at our location x equals -1, right? What does this look like? Here I am just giving away answers. Now, I probably will be gone for the night by the time we get that, but here are some other people that you should follow. Let me get back here. These are the 7, like, core math streamers who all kind of met together a few months ago, and so we all throw viewers each other's way, and every single one of us would absolutely love to help you out. So let me just do this one thing real quick, right? I'm in the UK right now, so it is 11:15 at night. Let me just do this real quick, right? If we were to zoom in on this particular thing, And now I want to do y equals, let's just do 1 times, this is going to be x plus 1, okay? And we're going to change this slope. Right? This right here is pretty closely approximated by y equals 6x plus 6, or 6 times parentheses x plus 1. This is a pretty good approximation for that. I think you'll probably agree because you can't see the blue one. Right? So if we go home, you could see that, okay, this is not the same function, clearly. This is a line, it's just linear, and this one's cubic. So they're not the same thing. But when you zoom in on the 0, on x equals -1, then they look pretty much the same. So locally, in this small area, this cubic can be approximated by a linear function, which means that at x equals -1, we have one side that's negative and one side that's positive. It's going to switch its sign. Right? If we had, like I said before, x plus 2 parentheses squared, right? At x equals -1, it can still use this. It could still be pretty locally linear. But at x equals -2, we can't find a linear function that's going to approximate this curve. It just doesn't work. So what do we have to do? This is going to be y equals -0.1 x plus 2 squared. Nope, too shallow. Okay, too shallow. So 2, 3, 4, 5, 6, 8, 12, 13, 15. There we go. So at x equals -2, this particular curve can be approximated by the parabola. -15 times parentheses x plus 2 squared. This is all about function transformations and stuff like that, which granted you probably don't have to do in your class, but I like to do it a lot in my pre-calculus class because it helps students understand like how functions are built and then how these rational functions can all fit together. Alright, so if we zoom back out and we get rid of the extra piece that I dumped in here, because that doesn't actually matter. And this is not part of it. This is not part of it. Right, what I want is this stuff. You know what? Let's do this. F of x is equal to this. G of x is equal to this. I want to graph y equals f of x divided by g of x. How about that? Right, this is the same thing that I drew, sort of. Right, we've got this part up here, which then crosses through -1, is negative until we get to 0.5, then it pops back up again, and then at 1 it goes back down again. So here we've got all this stuff over on that side from -1 back is going to be all in the positive region, and all the stuff from 0.5 to 1 is going to be in the positive region, and those are the two things we want to take. First year high school? Yeah. Yeah, no, that's fine. So it might just be algebra, and that's fine too, right? It's the United States system is very, very insular. It takes like all of the algebra puts it in 2 years, and then geometry, and then trigonometry, and then calculus, and it's very segmented. On the other hand, the British system, where my kids are going to be going to school, it's very much like, here's a kind of problem that we're going to solve, and let's look at different strategies to do it. And so they get all of the different kinds of mathematics throughout all of it. You know, they don't do calculus until much further on, but at the same time, like, they're still learning some more advanced topics in order to be able to solve different kinds of problems that are of their level. So it's very much more geared toward like cognitive development rather than just saying you're going to get thrown all this algebra all at once. So I'm interested in finding out where all the different stuff is going to be, but math and geometry, yeah. Sounds about right. Alright, so let me know if you have any other questions. Other than that, good luck on your English test. Yeah. It probably works for them in some way, shape, or form, so I know there's plenty about the American system that needs to change. Yeah, could be. Yeah. Alrighty. Good luck on your English test. Have fun. Go for it. Yep, no. Actually, my aunt is from Brazil. I don't remember exactly where. I think it's one of the smaller um, suburbs near Brasilia. I don't remember exactly, but yeah, it's been a while. Yep. Good luck. No worries. I'll see you around, I'm sure. Alright, if anybody else has any other questions, let me know. Got an ad break coming up, so we'll go for another couple minutes here, just chat, whatever, and then we're going to cycle water. I'm going to throw that away. And we'll see what everybody else wants to get up to once we come back from ad break. Or if you want to just throw stuff in chat, I will very happily respond to it afterward. All right. we're going to go ahead and press the button. Like I said, I'm going to throw that out, go cycle water, and meet you back here in 3 minutes. So thank you everybody for hanging around, and see you in a couple.
Lollipops, fresh in the morning. Welcome to my candy shop. Murukurate flavors on your lips. Sweet combination going on a bubble tea trip. Going on a bubble tea trip. Sugary no pick-up mix. Your eyes wanted me, I die. Skin up in the show, you know your knee. Floating on the clouds. What the eyes felt in my head, spinning round and round. Mirukurate flavors on your lips. Sweet combination going on a bubble tea trip. Fly away, sweet honey. Yeah, my energy. It's your demo. Fly away, sweet honey. Can I stay? Then my head spinning round and round. Going on a bubble tea trip. Sugary no pick-up mix.
Alrighty. Anybody have any ideas? What do you want to do? Now that I get back, the monitor says we're on ad break. Cool. Okay. So earlier we'd reduced our case and said by symmetry and just looking at like what's going to happen if we do certain things, right? AF is going to be shorter than any other possible AD that we have along that side, BC. And we can make the same argument for any other point, give or take. Energy and power. How do I phrase? Good evening and welcome. Oh. So, like, it kind of depends on what you're talking about. So, energy is just going to be like the amount of energy. No, Yup, I keep coming on circular definitions here. So, that's fun. Okay, so energy is an amount of, like, a force. So this is why it ends up being in joules or newtons or... Can it be in newtons? No, I'm going to have to look it up. Right, so you've got joules, which is the force of 1 newton acting through 1 meter. So it's the amount of energy that's being used to move something using a force. Right, and then you've got power. Okay. Okay. So energy is going to be like the ability to impart a force, whereas power is going to be the rate at which that energy is transferred. If you want something more like calculus level, then we're talking like energy is going to be our function that we're using here, and the power is going to be the derivative of that function. Right, the rate of change of the energy is the power. Yeah. No worries. Okay, so no matter what slice we pick that is parallel to BC, right, the point that we pick no, that's not going to work anymore, because we would have to draw those lines. Good news, they're the same. So we now want the point along AF, which is the altitude of A to BC. We want the call it F prime. We want, right, A F prime plus B F prime plus C F prime. It's going to be minimized. Good news. Good news, everyone. What's up, Sensation? Now BF prime and CF prime are the same. So this is going to be to minimize AF prime plus 2 BF prime. Without loss of generality, we'd have to do the same from all three perspectives. So I think this proves that it has to be the center of our equilateral triangle. Zerspel, have you ever used ChatGPT to explain a math concept? I did, in fact, try to use it to do some basic math problems, and it failed miserably. I do know that they have updated it somewhat in the last bit, so it might actually work a lot better. Have I ever used it to explain a mathematical concept? Not really, mostly because at that point, Thank you, Sensation. By the time that I got to possibly thinking about doing that, I had already gotten fed up with it. It was lying to me so much that I just didn't care. I had to correct it basically on every fourth sentence or something like that. It was just ridiculous. So I was no longer interested in it. I did, however, and this is kind of interesting, I did use it to say, make me a lesson plan for this topic. And it went through and basically just said, here's how to make a lesson plan on the internet. Start with a prior concept. Tell me how this, ask the students to do this. Show problems that do this. Give examples. Have the class work together. Come back together and explain the topic. And I was like, okay, that's at least pretty decent. Oh yeah, having it do technical work is absolutely out of the question. But if you ask it to do something general, then it can actually do it pretty well. Again, in my case, make a lesson plan. Then it knows how to follow that instruction, but it does not know how to do, or at least, a year or two ago, was having issues even doing the most simple technical problems. Again, like I said, it just lied. it said, here's how you do it. And it's like, no, you're making a number of mistakes. Let's just talk about this for a minute. And eventually it would correct itself, but like, it just wasn't worth my time. Yeah, yeah. I can't wait to get my videos scraped, though. Yay. Because you know it's coming. Okay, so if A is at 0, 0, F is just random point x, y, we were saying that this is going to be x squared plus y squared, take the square root. That's the distance for that one. Then plus twice the distance from unknown to 12 squared plus unknown to 0 squared for y. Okay, so 0 is equal to this. This is actually looking a lot better. Yeah, I can understand high school math being reasonable, which is one of the reasons why I transitioned away from using, like, procedural questions and started making much more of my questions conceptual. Students hated it, and I loved it 100%. I was like, okay, explain to me how this works. They're like, but. I'm like, no. I don't care if the computer can do it. I want to know if you can do it. I want to know if you understand anything. Or if you just let the computer do all the work for you and did literally nothing. That's 4. Zero equals. It's going to be 3x squared plus 2 by 2 is 4, 16x plus 4 is 16 plus 3y squared. It's not really helping, huh? Well, we got y by itself, so that's at least useful-ish. Y squared is equal to negative x squared plus 16 minus 16 thirds x minus 16 thirds. Yeah, it depends. At the moment, they have a cultural zeitgeist, if you will, that kind of pervades all of their endeavors and says, we should be efficient and come up with the best solutions and all that. So, at the moment at least, yeah, sure. Mm-hmm. Yep, and then when they get into jobs, they're like, what? What do you mean? What do you mean I have to understand things? Well, that doesn't work, does it? Because that's always going to be positive in the positive region. Oh, that's a minus 12. Not a plus 2. Yeah, that'd help. Okay, that's not that, and that's not that. Cool. Okay, that's going to be a 24 times 4. It's going to be a 96. And it's also going to be negative. And then here, this is going to be a positive 144 times 4. It's going to be a 576. 576 is divisible by 3, as is 96. Much better. Okay, this is going to be a negative x squared. This is going to be a plus 96 divided by 3 is going to be 32. 576 divided by 3 is 119, 192. So I'm using a drawing tablet. I had done Microsoft Whiteboard for a while, but I lost my Microsoft account because I left my job. So somebody else had pointed out Excalidraw, and you know, it serves my needs, so it's pretty good. B squared minus 4ac is 1024. Minus 4 times 192. Okay, so at least that's viable. 1024 minus, it's going to be 800 minus 32, 768. Right, so that's going to be 256, you're right, 256. Square root is going to be 16. Negative 32 all over 2 times negative 1. Which is going to end up being a square root of all that. 16 plus or minus 8. 24 and 8. $24 does not exist within any of this, so that's just not going to work. Y is going to be 8. That is not what I was expecting. Alright, cool. That's... No, never mind. We're good. It's a square root of those. Right, or the square root of 24, which is 4 and change. I'm liking 2 root 2. 2 root 6, maybe slightly less, but I think that also makes sense. Alright, if y is equal to these things, then y squared can be 8 or 24. So if it's 8, you get negative x squared plus 32x minus 192 is going to be x squared minus 32x and plus 200 equals 0. Or 24 is equal to negative x squared plus 32x minus 192, which is going to be x squared minus 32x plus, right, 8 comes off there, it's 216. Hey Suki, I'm sorry. Completely not paying attention. I apparently thought it was pretzel rocks or something. HMC.edu calendar Nelson speaker series, very nice. John Warner, Resist, Renew, Explore, Human Values in the Age of AI. Emily Bender. Sal Khan, ooh. September 10th. I think we missed that one. Curses. Is there a particular order to these? Also makes sense, since there's only 3, it doesn't... Negative x squared. I would have liked to have been on that one. I have liked his talks especially. Nah, x squared minus 32x plus 200. And plus 216. Yep. So x values that then need to be square rooted, I think. Oh no, those are just x values. 8. 8 is within bounds. 12 is the upper bound, so no. So 8.51669 for 200, yeah. Not 0. 8.51669. And y is equal to the square root of 8, which is, come on, I should know that. 2.82. Oh, right. 2.828. 427. Well, that's not very, like, equilateral triangle-y. Certainly not the center of the triangle. And the other one's 216. Doesn't change much. 9.67, yeah. Six, 7, 5, 4, 4. And y is equal to square root of 8, again, still. So 2.828. 427. Stuki, this one's right up your road, so I was looking at the Harold Jacobs book, Geometry, and right at the beginning he had a puzzle that Euler had done, thousands of years ago, whatever. At least I think he did. This could just be a problem from antiquity without his Euler. Not Euler. Euclid. The elements. This might actually just be a problem from Jacobs, but it's a classic problem, so it doesn't much matter. Basically, a ship is wrecked in a storm at sea, and only a couple members of the crew survive. They both get to a desert island and pass out, and then one the next morning decides that he is going to spend every single day going to one of the 3 points, A, B, or C, along the triangular island that they are currently stranded on. It is equilateral, approximately, and 12 kilometers aside. He's going to go to each of the points through some process, no idea what. And then in doing so, he is going to try to spot a ship out on the horizon and then light fires, whatever. The goal here is that he is going to place a hut somewhere within the triangular space that is allotted to him, such that any location he wants to go to, A, B, or C, directly from his hut, the sum total distance is then minimized. So we have F prime here in the middle of the triangle, which is going to be where the hut is, and then he is going to cut direct swaths through to A, B, and C, and we want to minimize the sum of those three distances. So my intuition was, okay, if he's parked on, we were going to focus on BC as being, like, since it's an equilateral triangle, right, without loss of generality, we could just say, if he parked it on one of these sides, then there is going to be an equal and opposite point, such that he's going to have the exact same distance just on the opposite side of the altitude, AF. And also then, AF, the altitude, is going to be a shorter distance than any of these other lines that meet BC at an angle other than 90 degrees. Then we wanted to know if we decrease the length of AF by some amount, right, then the slack is going to get picked up by both BF prime and CF prime. And there's got to be some way in which it's going to minimize the distance such that AF prime plus BF prime plus CF prime is going to be as small as possible, because any changes in the distance or in the length of AF prime are going to net in a very small change initially from BF to CF, the original F that's in orange. And consequently, this means that despite adding two new lengths, BF prime and CF prime, it's going to cause yep. God. It's going to cause us to lose more in AF than we are gaining in BF prime and CF prime. So initially, at least. And then we have to figure out where that point's going to be. I said it has to be along AF, but I'm not sure that that's true once we come off of... I get the feeling that is true, but... yeah, I'm just not 100% sure. Anyway. Hey, welcome back. How'd it go? I hope reasonably well. Yeah, so that's what I was thinking as well. Is that it had to have been one of those, you know, one of those special ones, and then it would have to be bisymmetry. I didn't know if it was if it wasn't an equilateral triangle, if it was going to be the orthocenter, but I don't know if that's the right word. So yeah, welcome back. I can maybe answer a couple more questions, but I think we're probably running out of steam here. We'll probably head over to see Dr. Gold, who is at Actual Education. Absolutely. Well, I mean, if you want to ask more than that, that's fine too. But oh, I don't remember which one's which either, Stooky, so... Yep. That's the thing. Alright, so what do you see for that one? Well, sort of. Okay. So, the solution being that x can be all real numbers is definitely different than the last one. Right? We had... that the domain was all real numbers, which is also the also true here. But we did not have that the solution was all real numbers. Right? Last time we had a solution from negative infinity to -1 and a half to 1. Yeah. So in this case, all real numbers will end up giving you a fractional value, if you plug it inside that fraction, of less than 0. Negative numbers. Okay. So like we were doing last time, what you're really looking for is where are these values changing sign, right? Where is it that we can end up shifting from positive to negative values or negative to positive values, right? So if we have x squared minus 2x plus 2 divided by negative x squared minus 2 is less than 0. So the first thing that I usually do is I treat this as an equation. So again, if you're going to do this, right, x squared minus 2x plus 2 all over negative x squared minus 2, set it equal to asterisk 0, which is, that's not a real thing. It's just, to me, reminding myself that I've got something else that's not quite what I'm actually looking for. Right, you're going to multiply both sides by negative x squared minus 2. Right, so on the left the denominator's gone, and then on the right it's still 0. So now x squared minus 2x plus 2. So, Bhaskara? I mean, I don't know what the what that one is exactly. Kakraval method? That's quadratic formula. Gotcha. So yeah, once you get to this point, then that is the way to do that. So if you're looking at this and trying to, again, if you try to factor it, it's just not going to work. Right? You need factors of 2 that are going to have the same sign, first of all, and then add up to -2. It just doesn't work. So there are no rational solutions which are going to make this work. So we say, okay, irrational numbers are next. So yeah, negative b is 2 plus or minus the square root of b squared is negative 2 squared is 4 minus 4a times c, which is 2, all over 2a. This is going to be equal to then 1 plus or minus, right? The inside here is going to be 4 minus 8, so that's going to be a negative 4, which then we can have this be a square root of negative 1 times a 2 out front. And actually, right, we divide by 2, so that's gone. So this is 1 plus or minus I. I is defined as the square root of negative 1. Anybody who doesn't know, there's a whole bunch of rules and stuff that go along with that. However, the most important point is that this is not a real number. Right, so 1 plus or minus the square root of negative 1 is not going to give us any sort of value that makes any sense for this particular problem. Which means there are no zeros for this function. Yeah, right. So solving the quadratic equation is going to allow us to find any zeros in the complex plane. So Bhaskara is a Indian mathematician. Siddhartha? No. Bhaskaracharya, or Bhaskara II, is one of the greatest mathematicians of all time. And he does all sorts of other he was able to come up with a whole bunch of really cool stuff, including, as you said, the we call it the quadratic formula, which is this bit here, right? Saying that x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Yeah, quadratic. So with no zeros, there is no sign change from zeros. Okay, so then we have to look at the denominator and say how many sign changes are potentially there from discontinuities. So negative x squared minus 2 is equal to 0. And here that's just going to be x squared is equal to negative 2. And that doesn't really work with being compatible. Our x is going to be equal to a plus or minus square root of 2 multiplied by I, square root of negative 1 again. So there are going to be no discontinuities. And with no discontinuities, there's going to be no sign change. Product inequality and quotient inequality. I mean, I think just what I'd said here is that you're going to always look for, to the 1 grade, exponent. Is that what you mean? So, I mean, no matter what you're doing with inequalities. Yeah. You can use this. It's alright. You're always just going to be looking for where it is that the sign changes occur. So when you have an inequality, you always just ask yourself, where can the sign changes occur? Well, it's either when the stuff on either side is equal to each other. In this case, this whole fraction is equal to 0. Or if there are discontinuities. Like, those are the only two possibilities. Either the function is discontinuous and it jumps, or these things are equal to each other. So find all those places. Where are they equal to each other? Where are there discontinuities? Once you do that, you can draw out a number line or make your table or whatever else. So Satari, I don't know exactly where you're going with it, but X values and Y values? Knowing where the min and max values are on your calculator is helpful. If you want to, you're not going to be able to figure it out algebraically. The only way to figure out where min and max values are algebraically is by using calculus. So you're not there yet. But if you're using it on your calculator, or if you have a different method to find it, so the minimum and maximum values for f really don't make a difference for what we're doing. Right? What we're doing here is we're saying, where are the zeros of this function and where are they discontinuous? And once you find them, all we care about is whether it's positive or negative. We don't care about what values they have. We don't care about where they are. It's just, is it up or is it down? In this case, we want everything that's down, right? We want all the negative stuff. So if you're trying to find the properties of the function, then yes, min and max values matter. For quadratics, then you're right. You're trying to find right, y equals 4x squared plus 2x minus 2. here, if we're trying to find the vertex, then we have a special formula for it, right? X is equal to negative b over 2a, and y is equal to, take that function and plug in, or take that value and plug it in. So plug it into the original function. That's how you get that back. Oh, okay. Abscissa is the x coordinate. Okay. Sorry. No, I just have never heard abscissa an ordinate. No, no worries. So there's kind of a good thing to know about the abscissa specifically, and that is that we have this right here. Right, so our x is equal to negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. Abscissa of a vertex. Oh, man, if only I had the best viewers, but I already do. Bam. Yep. Oh, there wasn't that. Okay. This part here is the abscissa of the vertex in your quadratic formula. So if you're taking the whole quadratic formula, just the first part of it, negative b over 2a, is the abscissa of the vertex. And this stuff, the second part, the square root of b squared minus 4ac all over 2a, that is telling you the distance away from that your zeros are. I'm not sure what delta is. Okay. B squared minus 4ac. Um, in this case, no. It is negative 4. Oh, that was a 2 coming out. Right, but then it got divided by 2. We're good. Never mind. Yeah. So 4 minus 8 is going to be a negative 4. So our delta in English is called the discriminant. So the discriminant is negative 4. eh. Okay. Cool. Yeah. I mean, I think we might occasionally. Depends on who you ask. Let's see. I don't think I've ever used that. So here this is B. It looks to me like you're writing delta twice. One with and one without shortcut notation. Negative delta times b squared minus 4ac over 4a. Yeah, I don't really know what that is referring to. We have a y4a. Is it inside the square root? In which case it should probably be 4a squared. Unless that is the... It's fair. X of the vertex and Y of the vertex. Okay. Yeah. Uh-huh. Slide number 3 specifically. Mm-hmm. Yeah, no, that's okay. It's just what you get when you plug stuff in. Yeah, it's fine. Alright. I'm gonna need to get going here because I'm fading fast. So, but thank you everybody for coming in and hanging out and doing some math tonight. So I thought I'm sorry about tonight, but we can, if you go over to Penn Center's Discord, more people will be happy to answer questions there. It's getting on to be almost 1 o'clock here, so yay. And we'll be back for mathy type stuff, somewhat soon-ish. I guess it might be until next Tuesday, but most likely we'll do it before then. And then we're going to do gaming type stuff on Friday, possibly also sooner, depending on how I feel about stuff. And anyway, we're going to go see Dr. Gold. So hang on in here if you're interested in going to go see his. Usually he does SAT prep, so asks lots of questions about cool stuff that you might end up seeing on like standardized tests and whatnot. If it's not for you, that's fine. We got a few other people who are also doing math. Go check out the math tag, and hopefully I'll see you all later. My name is Obi-Wan Pez. This is N Simplex Pachinko. See you later.